Once again, welcome everyone to Advanced Function class. In the previous class, we covered two topics, which are average rate of change as well as instantaneous rate of change. And we learned a few methods of defining average rate of change on an interval and approximating the instantaneous rate of change by means of shrinking interval method, where we make the area where we look into our change of function. For example, this is our coordinate axis and we have curve like this, and we would like to know the instantaneous rate of change at this point. So we usually, for average rate of change, we have two different points. In this case, in order to estimate the instantaneous rate of change, we move one of these points or both of these points closer to the points that we're interested in, exactly here where we have x value. So that's the biggest part of advanced functions that you have to know by heart and be comfortable with it. So, and that's what we're gonna have our test based on. We're gonna do it this Sunday. Friday is basically additional class when you can ask me questions. We're gonna cover a little material, but most of it gonna be dedicated to helping you figure out everything that you may be missing in these units. Okay, and is there any questions at this moment, organization questions? Hala, Rana, any questions? Okay, great. So get familiar with what we have here on the desk. I'm gonna get back to you in a minute. Okay, thank you for information, Mustafa. So let's get to the material. So what we are doing here is trying to understand how instantaneous rate of change is reflected on the graph that we are studying. Okay, and up until now, we learned these little methods of how to estimate the instantaneous rate of change. We know our beautiful formula delta y over delta x, which basically means difference of the dependent variable with respect to the dependent one. And we use this formula to approximate instantaneous rate of change as well by making our denominator close to 0, for example, by making the delta x literally small number that we can say it's equals to 0, or we can pick two values that are extremely close to each other and see the estimation to a certain degree. But what does it really means for us graphically? What does the instantaneous rate of change shows us? And that's what we're going to discover today. If you remember, when I was talking about the average rate of change, we looked into it as such a line which called a second line that joins 2 points on the graph as so, and this would be called a second line, and this second line represents the average rate of change of the function in this interval. If to be more exact, the slope of this line with respect to x-axis would give us the rate of change of this function. If you remember, we also identified the rate of change delta y over delta x as a tangent of an angle alpha, right? Because if you will look into what this triangle consists of, it's nothing more than change in x-axis, x1, sorry, x1 and x2, this is our delta x, and here we have change in y-axis, this is our y2 and y1, right? So by finding delta y, y2 minus y1, divided by delta x, x2 minus x1, right? We basically calculating the ratio of the opposite side with respect to the adjacent one. And that's exactly tangent, isn't it? So basically we're identifying the tangent of this angle that joins 2 points together and thus giving us the rate of change. The steeper this line is, the bigger the angle is here, the higher the rate of change of this function. Do you understand what I'm saying here? So basically these lines that we're drawing, the steeper this line is, the higher the rate of change. For example, if we join 2 points at this part of a graph, which represents some kind of exponential function, we join these 2 points and you can see that angle here is much steeper, right? That's what we should understand about rates of change. But these examples are average rate of change. What about the instantaneous rate of change? So let's look into it. So goal, to estimate the instantaneous rate of change using slopes of lines. Exactly this is called a slope of line. So in the previous lesson, you used numerical and algebraic techniques to estimate instantaneous rate of change. Graphically, you have seen that the average rate of change is equivalent to the slope of a second line that passes through 2 points on the graph of a function. That's correct. How can you use slopes of a second lines to estimate the instantaneous rate of change? Again, basically approach that they suggest here is equivalent to what we did in the previous class using tables, right? When we estimate the average rate of change on an interval from 1 to 3, right? Then from 1 to 2, then from 1 to 1.5, from 1 to 1.1, from 1 to 1.01, and so on. And the closer we get in these 2 points, the more accurate would be a second line representing our instantaneous rate of change. Let's try and visualize it right now. It's not so hard. You don't even need a graphical calculator. So I'm gonna sketch a new graph that has x and y-axis. And on this graph, I'm gonna sketch x squared function. And x squared, as you may know, is just a parabola that goes through 0, x 0, 0, x, y 0, 0, with its vertex. I'm just gonna sketch a little bigger coordinate axis like this, and as such, y, x, and parabola. Yep, I hope I did my, no, it's not so symmetrical. Let's try again. Yep, now it's good. So we have our parabola x squared. This is our function x squared. And enter the function f of x squared into the equation editor of your graphical array, graph it, and draw a sketch of the graph. We did it. On your sketch, draw a second line that passes through the points 1, 1, and 3, 3. So x coordinate equals 1. Oh, hello, Safa. No worries. Thanks for joining. Please, if you have any questions, feel free to ask. So we're talking about the instantaneous rate of change in graphs, how it's represented graphically. So here we have a function x squared, and we are asked to sketch a second line. As we spoken previously, second line is the line that joins 2 points on the graph. For example, here it would be just a straight line joining these 2 points. And we have to join 2 points that are having coordinates x equals 1, and y coordinate is the function from x equals 1. So let's say 1 would be here. Let's say 2 would be here. 3 would be here. So x equals 1. We draw, let's use the blue color. We can say we can draw a line from here to this point. X equals 1. And f of 1, x squared when x equals 1 equals 1, right? Y equals 1. So here's our first point. And 3, x equals 3. And function when x equals 3. X squared when x equals 3 is 9. So our 9 would be here. And this is our 2 points that we're going to join with the second line. Okay? So now we have certain straight line with a certain slope that we can evaluate, because the slope of this second line is tangent of this angle. So tangent alpha, let's call this angle alpha, equals delta y over delta x. Delta y is here, and delta x is here. Okay, let's leave it as such, or you want to evaluate it. It's not so hard. Delta y, 9 minus 1 is 8. It's important that you substitute the beginning from the end, because this affects the sign that your tangent may have. If, for example, if you subtract 9 from 1, you're going to get negative 8, which means that your function is decreasing if your denominator is positive. But that's why you subtract beginning from the end. So x2 minus x1, y2 minus y1. In numerator, we're going to have 8, 9 minus 1. In denominator, we're going to have 2, 3 minus 1. So the tangent of this angle is 4. This is our slope. Great. And now we have to calculate the slopes of the points that are gradually getting closer to the point of our interest, to 1, when x squared equals 1, right? Uh, so let's take point x equals 2, right? Here, x squared would be equal to 4. Now between 1 and 2, tangent alpha delta y over delta x between 1 and 2 gonna give us delta y is 4 minus 1 is 3 divided by delta x 2 minus 1 is 1. Tangent alpha equals 3. Okay, now we go even closer. Now we go 1.5. This much closer. If you excuse me, I won't keep drawing on this graph because it's getting really tight. And that's the reason why we're doing it. So you can imagine that as if the second line that we are drawing, so let's say for this one I'll use purple color. Well, for this one I use green. That joins 1 and 2. You see the slope, now slope changes, slope a little less. From 1 to 3, slope was greater, so the rate of change was higher, the average rate of change between those 2 points. Now next point, let's say, is going to be 1.5, somewhere here, 1.5. So you got the idea. And we're going to get closer and closer, like, to this point, 1 and 1. And then this point, basically the slope of our line is going to be as such. It's going to be a tangent line to this point, right? It will be tangent line. Tangent line is such line that touches the curve only at one point. So you see how many slopes can we draw through this point 1? One is higher, the other one would be even higher. We're going lower, lower, until we get to the instantaneous rate of change at this point. So if we keep evaluating the slope of such line and we get to 1 and 1.01, we would get the tangent alpha equals delta y over delta x, which equals to delta y. Let's look into it. Delta y, for when x equals 1, it's 1, and when x equals 1.01, let's use our calculators, 1.01 times itself, because the function is x squared. We're gonna get 1.01 squared. We're gonna get 1.0201. Let me move away. So if you excuse me, I'll continue solution here. So 1.0201 subtract f of 1, right? When x equals 1, and x squared when x equals 1 equals 1. So subtract 1 divided by delta x. X was 1 and became 1.01. So 1.01 subtract 1. Okay, let's evaluate it. We're going to get 0.0201 divided by 0.01. And that's equals to 2.01. And as such, we now seeing that the approximate instantaneous rate of change at point 1 would be equal to 2. You see, the smaller step we make, the closer we get to this value. Now we have to create a formula for calculating the slope of any second line that passes through point 1 and general point x. And it's not so easy. A slope of a second line, as we defined before, is a tangent of delta y over delta x, right? So basically this is our starting point, and x point with x value, with some arbitrary value x, is going to be our second point. So if we write our tangent alpha, our slope of a second line, of wherever 2 points, what we're going to see is that it's delta y over delta x equals to f of x minus f(01), yeah, finishing point minus starting point in y coordinate, and now in x, finishing point, which is x minus 1, because 1 is the starting point for x coordinate. So this is our general function, formula basically, to calculate the slope of any second line that passes through function when it equals 1, and general point x when function equals f of x. Now you can substitute the actual function here to finish this up. So what we're gonna see is that f of x is x squared, right? So x squared subtract f(01), f(01) equals 1, divided by x minus 1. So x squared minus 1 divided by x minus 1. That would be our formula for calculating the slope of any second line. Right? This is what we did in all of the previous steps, but for 2 specific points. And this, how we can express the general formula that we use every time. Is there any questions about this? A, B, C, D parts of this exploration? Any questions at all? Am I that good? Oh, hello everyone, whoever just joined. Come on guys, get involved in the class. Let's make this time interesting for all of us. Ask questions, because I personally think that if you understand this, and you understand this really well, then your entire future at university, math, etc. is going to be much easier, because that's what all analysis in mathematics is based off. The slopes, the parameters of a function, how they change, and tangent of a second line is very important parameter. Do you have any questions on how to sketch the second line, on how to represent the instantaneous rate of change in a function, how to estimate it using slope of a second line? Do you have any questions about that? Okay, that's great. Do you need time to finish copying down? Okay, I'll treat it as no and we'll continue. Mm, so basically, what you're gonna see by doing the same procedure, but now moving from left to right to this point, right? Before, you see we moved from right to left. We've been shrinking this area for second line from right to left. Remember shrinking method from last class. But in the next example, right after, we're doing exactly the same procedure, but from left to right. And if you look at this graph, I'm going to clear it a little bit. If you look at this graph and we move the other way around now to this point when x equals 1 and y equals 1, now we go from left to right. And from point x equals -1, we're going to see that first slope is going to be 0. There would be no change between these 2 points. It would be just a horizontal line joining x minus 1 and x1. And that's quite interesting. So it means the average rate of change between these two functions is 0 because the y value didn't change from -1 to 1. But it's not true. We know that it changed in between of those 2 points, right? We can see that basically that it was changing. So average rate of change, as I've said before, it's only average. So what you're gonna see here, that the closer we get to point 1, the more second line is gonna get closer and closer to the tangent line we got in the first example. I'm going to use a red one for this, where we were moving closer from the right side. You see? Another straight line. Another one here and here until it gets same with this blue line. That's where the instantaneous rate of change of this function at x equals 1. You see here, we do exactly the same steps, but now moving from left to right. Our x coordinate changes from from 0.99 to 1. In the previous example, it was changing from 1 to 1.01. This is step of 1/10. And basically what you're going to see that the slope of a tangent line moving from left to right is gradually changing and getting closer and closer to the true value of instantaneous rate of change. An instantaneous rate of change is represented by a tangent line. This is very important. So tangent line, a line that touches the graph at only one point. Let's call it P. Within a small interval of relation, it could, but doesn't have to cross the graph at another point outside the interval. The tangent line goes in the same direction as the relation at point P, called the point of tangency. So point of tangency, it has on this specific touching point where it shares one coordinate with the graph. So we can verify our estimate that we did before by sketching a tangent line to the point when x equals 1. And this is going to be our parabola. And when x equals 1, here, our tangent line would look like this, right? Touching my graph only at one point. Let's call this point P. And if we're going to repeat the same procedure for any other point on the graph, for example, moving from right to left with these 2 points, and then moving from left to right with these 2 points, eventually we're going to get to the point where we get only one tangent line. It's going to look like this for this point, or for this point, for example, going to look like this, almost vertical. For this point, it's going to look like this, and so on. So now we know how to identify the instantaneous rate of change graphically. Here you can see a more clear picture of what it looks like. You see this point P that we are interested in, and this is method of getting closer to it from left to right. You see, from Q1 to Q2, from Q2 to Q3, and that's how we're getting closer to the tangent line. You see, this is the tangent line that we are talking about, the red one. And on the other hand, we're doing exactly the same thing, but moving from right to left. From right to left. And again, the red line represents the tangent line that we're eventually gonna get, as well as on the drawing to the left. This is very important, I'm telling you. So the slope of a second line is equivalent to the average rate of change over the interval defined by the x-coordinates of the 2 points that are used to define the second line. The slope of a tangent at a point on a graph is equivalent to the instantaneous rate of change of a function at this point. And what do you need to know? That the slope of a tangent cannot be calculated directly using the slope formula, because the coordinates of only one point are unknown. That's why we were doing all of it, by getting closer and closer and closer, but we could never actually shrink this interval to a singular point. This is the job of another part of mathematics or calculus, and you're gonna see that there. But here, we are not saying that it's only one point. It's basically 2 points that are really close to each other. The slope can be estimated, however, by calculating the slopes of a series of second lines that go through the fixed point of tangency P, and points that are get closer and closer to the fixed point Q1, Q2, and Q3. In the drawing, you can see as Q approaches P from the left, the slope of QP increases and approaches the slope of a tangent line. On the opposite side, as Q approaches P from the right, the slope of QP decreases and approaches the slope of a tangent line. So what do we have to understand here? Then when curve of a function looks like this, generally, you understand that this function is increasing, right? It's getting bigger and bigger, and you can see that the slope of a line that joins 2 points on this graph getting gradually steeper and steeper. But if you approach, for example, this point from right to left, you're gonna see that the slope of your line is decreasing. But on the other hand, if you approach the slope from the left hand, it is increasing, isn't it? Because this general area is increasing function, right? On the other hand, if you would have same example but with a decreasing function, you're gonna see that this graph from left to right, the slope is decreasing on the counter hand to the previous example, right? And on the right hand side, if we move from right to left, we can see that the slope is going to be increasing. This is, for example, in a decreasing function. Or left-hand side of function x squared, because function x squared is parabola that looks like this. So one side is decreasing, another side is increasing. This is important to understand to work with graphs in your home assignment. Does anybody wants to try solving a problem in the class? I'm not insisting, but it can give you extra points. No, nobody? Not a complicated problem, and I'm gonna help you. Just evaluate a few slopes. Because you're gonna write your final, not final, your test based on this topic, so maybe you can figure something out. Question number 3, set B. Not all of them, but just evaluate the slope in each function at the specific point. So for example, quadratic function, when x equals 3, give slope of a tangent line basically at this point. Anybody wants to try and explain your approach? Come on, everyone, we could have already done it. What are you waiting for? It's 1 minute problem. Okay. But then you promise that each one of you will do at least one on their own. So let's solve for number 1. So as we've seen before, the way we're doing it, we relate the tangent of angle alpha, basically the slope of this line, which delta y over delta x. Okay, that's the first thing. Second thing that we learned, that we have to make this delta x comparable with 0, approximately 0, right? So we want to make this change extremely small. But one of these points that we're taking in our method must be the point of tangency, the point that we're interested in, for example, x equals 3. Okay, so let's do that. Let's take x equals 3 and one point to the left or right from x equals 3. On the graph, it would be represented as such. This is y-axis, this is x-axis. Let's say this is some quadratic function that should look like something like this, watching down because of the leading coefficient, which is negative. This is what we covered in one of the first classes, okay? And point x equals 3, let's say here. I'm not sure if it's exactly here on the graph. This graph may be a location like this or like this. I'm not sure. This is just a sketch. And now I take one point or from the right or from the left. And this point must be super close to 3 in order to fulfill this requirement. The delta x is very small. So let's take 3.001. That should be sufficient for us to estimate the slope of this graph at this specific point. So now I will add my tangent alpha delta y over delta x, where change in y-axis is my function f of x, right? F of x2, my second point, subtract f of x1, my first point, divided by x2 minus x1, which equals to f of x2. x2 is 3.001. This is my function. So I write negative 3.001 squared, right? And it should be like yep. First we raise it to the power and then we add minus in front of it, plus 3.001 times 6, subtract 4, minus, right? Because here we have minus f of x1. And what is x1? X equals 3. Now, minus, open the brackets, minus 3 squared plus 6 times 3 minus 4. And all of this divided by 3.001, subtract 3. What we get is 3.001 squared is how much? 3.001 squared equals 9 minus 1, 9.006, and that's enough. 3 digits is more than enough. The calculator shows me 001 after this, but we don't need it. Plus 3.001 times 6 plus how much is this? Is this 3 times 6 is 18, so 18.006 minus 4 minus, because here in formula we have minus this function, but now x equals 3. Negative 3 squared plus 6 times 3 minus 4. Let's calculate it all together, not to waste so much space. So minus 3 squared is 9, minus 9 plus 18. So 9 minus 4 is 5. But we have minus in front of the bracket, so altogether it brings us to minus 5. Do you agree with me? Anyone? Okay. Make sure my calculations are right. So 0.001 in denominator, because 3.001 minus 3. Residue is 0.001. Now we have to calculate our nominator, which is negative 9.006 plus 18.006 minus 4 and minus 5. And I got very interesting stuff, guys. This nominator altogether equals 0. So I got 0 divided by 0.001, which gives me 0. And my tangent of the slope at this point equals 0. So it means it should be a simply horizontal line, not as I sketched it here. It should be a horizontal line, which means this is the vertex of my parabola. It would be just a horizontal line here. And that's my tangent of this function when x equals 3. And you can check it. Indeed, x equals 3 is going to be a vertex of this quadratic function. And this brings us to another interesting property of instantaneous rate of change. Now we know whenever instantaneous rate of change of any function equals 0, it means this is the minimum or maximum value of this function. Remember, exponential function, they have many peaks like this. And in every peak of the function, we're going to have instantaneous rate of change 0. And not only peak value, the maximum value, but also the minimum value as well. Isn't that cool, guys? Now we basically came up with this thing, such as instantaneous rate of change, and we got a property of the instantaneous rate of change right away that's gonna help us a lot. You found the relation between the equations on set A. What is the relation, Safa? Yes, great job. That's exactly what it is. For example, for a function j of x, it equals 5. And what would happen if you sketch function when it equals 5? It would be just a horizontal line that passes through point y equals 5 and goes like this, right? And slope of this line anywhere between any 2 points, even tangent to one of those points, would be just a horizontal line with slope 0. And Safa, you're absolutely right. Slope for all of them would be 0. Did you calculate them, Hala? And what's common between them? So basically, it means that in set B, all of these functions are increasing at x equals 2. Isn't that correct? Yes. And for set C, every function at the given point is decreasing, so going down like this, or going up. Great job, guys. I'm really proud of you. As for me, this is a good level of understanding that you're showing. And if you're doing so great, why don't you solve one more problem for me? And we're gonna have a break for like next 10 minutes, okay? So you all must be able to use annotation on the desk. Can you test it out? Can you use your pencil and draw something? Please, guys and girls, can you try using your annotation tool in the bar on top? You should be able to write as I do, like this. Okay, wherever. So let's make a break, and while this break, please think about question number 5. And I'm gonna ask one of you what you think about it. Yes, in Zoom you can use annotation tool and draw. But for now, let's make a 10-minute break, and meanwhile think about question number 5. What is how are the two calculations similar and how are they different of the average and instantaneous rate of change? Mhm. Okay, guys, is everybody back? Okay, I can see that somebody's doing a nice graph right here. So I believe this graph to the question number 4. Okay, have you thought on question number 5? So I will answer this question. So what's different in calculations of estimating average and instantaneous rate of change? The main difference is that when we calculate the instantaneous rate of change, we are not calculating the exact value because we are unable to do so. Because the denominator cannot equal to 0, but can just approach it to be close to be equal to 0. And so calculations of instantaneous rate of change are approximations. And also, difference in calculation is as follows. For average rate of change, we need at least 2 points. For instantaneous rate of change, on the other hand, we use only 1 point. The second point we choose on our own will. Oh, Hala, thank you for your answer. Yeah, and both find the slope. That's correct. And difference, yeah, pretty much what I've said, but in another way, but it's correct. Thank you, Hala. Great answer. But next time you can use your microphone to give an answer faster. But thank you for your work. It's really good. Any questions about this? Question number 4. So what you're gonna see that the change in value is not constant. For example, here is a big leap, here it's smaller, then it's same, then it's smaller and smaller, smaller. So function is losing its speed of growing. So I would say this curve looks something like this. Yeah, of course, on a greater span, it should be something like decreasing line, like higher, same, then becoming smaller and smaller and smaller and smaller. If you would plot each of these points as such, you would get much better representation of what this graph looks like. So we have to remember that we have a second line that joins 2 points, and tangent line is a line that touches the graph in only 1 point. How do we determine the average rate of change? Here's the function. You can refer to it whenever you want. Make sure to memorize it. It's even better. It's not a complicated function. Here is one of the methods of calculating an average rate of change using difference coefficient, h, where we make h the change in points. Sorry. So we also remember that slope is a tangent of an angle of in the specific point or between 2 points. And we know how to calculate it using the average rate of change formula. Overall, you can use this as a preparation for your test, because most of these questions are going to be in the test for this unit. So now let's take a look into another chapter of using rates of change. Now, this time we're going to create a graphical model. We're going to represent verbal descriptions of rates of change using graphs. So let's say somebody explains you how something changes with respect to time in words, and we're going to convert it into a graph function. So today Steve walked to his part-time job. As he started walking, he sped up for 3 minutes. So first 3 minutes of his walk, he was increasing his speed. So the function should be increasing. Then he walked at a constant pace for another 2 minutes. So for 2 minutes, just straight horizontal line, because he was not changing his speed, right? 2 minutes walks at the same pace. When he realized that he would be early for work, he slowed down. So he started decreasing his speed. His walk ended um, and he came to a complete stop once he reached his destination 10 minutes after he started. So for last 10 minutes, so this is going to be 10 minutes interval. This is, let's say, 2 minutes interval. Don't look at the scale. It doesn't matter right now. And this is a 3 minutes interval. So overall, he spent 15 minutes to get to work. First 3 minutes, he was accelerating. So the graph of his speed with respect to time is growing. And for 2 minutes, he was walking at a constant pace. So we have a horizontal line. And the following 10 minutes, he was decreasing his speed. So we have a declining line. So what would the speed versus time graph of Steve's walk to work look like? And that's a more clear representation of what I just showed you. And you can clearly see the interval where he's speeding up from 0 to 3 minutes, then from 3 to 6, from 3 to 5, he's walking at a constant pace, and then from 5 to 10, he's yes, so because he reached his destination 10 minutes after he started. So overall, he was walking for 10 minutes. So last interval is 5 minutes. So because Steve was speeding up, his speed is increasing as time increased. His speed is increased at a constant rate, so the graph should be a straight line with a positive slope that begins at 0, 0 and ends at x equals 3. Between 3 minutes and 5 minutes, Steve walked at the same rate, so his speed didn't change the graph. No, so his speed didn't change. The graph should be a horizontal line that connects to the first line. After 5 minutes, Steve slowed down at a constant rate, decreasing his speed as time increased, so you might draw a straight line with a negative slope that begins at x5 and ends at x10. So again, slope of a second line or tangent line at the first interval is constant because he was spinning up at a constant rate. He was changing his speed gradually with respect to time. So tangent line or slope of a tangent line at this point is always the same. Then the slope of a tangent line turns into 0 because he's walking at a constant pace, just horizontal line. Then tangent of the slope becomes negative, equals negative number because he start decelerating or decreasing his speed also at a constant rate. So it's straight line. Okay. Now we will assume that Steve, was walking at a variable speed. So let's say he's not able in reality to accelerate at a constant rate all the time. He starts slowly, then he's gradually increasing his speed faster and faster. And then same stuff when he decelerating. He can start decelerating fast, but he will be slowly finishing his stop, right? You never run and like instantly stopping, right? It's not possible. You do it gradually. So because Steve was speeding up, his speed increases as the time increased. You can see that this part of a function represents the increasing function. His speed increased at a variable rate. So you might draw an increasing curve that starts at 0, 0 and ends at x equals 3, right? And now, second line between 2 points will be always different on this part of the graph because its average rate of change is not constant. Furthermore, instantaneous rate of change would be different too. You see, the tangent line will be different for each point. So between 3 and 5 minutes, he walked at the same rate, so his speed didn't change. The graph should be a horizontal line that connects to the first line. And after 5 minutes, he slowed down at a variable rate, decreasing his speed as time increased. So you might draw a decreasing curve that begins at 5 and ends at x equals 10. Is there any questions about this example? Okay, I suggest it means no. So let's reflect. Which details in the given description were most important for determining the shape of the graph? Most important was the time interval when he did so, and what was he doing in this time interval, and furthermore, how long is the whole range of this function is. So here we know it's from 0 to 10 minutes, and then he was slowing up, speeding up, etc. And furthermore, there are more graphs that can represent Steve's walk. For example, instead of this graph, for example, he could speed up in another way. For example, he would speed up like this. He would speed up incredibly fast at the beginning, and then he would slow down. Same one he could did with his deceleration. He could decelerate slowly at the beginning and start decelerating faster later. Okay? But the middle part where he's running at a constant pace is only like this, only straight line. Now example number 2. A flask, a beaker, and a graduated cylinder are being filled with water. The rate at which the water flows from the tap is the same when filling all three containers. So basically speed of filling up is the same for all three flasks. So draw possible water level versus time graph for the three containers. So let's try and do that. I'm gonna use blue color. So this is time versus water level. Let's say water level, let's say we're gonna represent it as height, right? This is gonna be our height. How high is the water in the container? And this axis will be the axis of time. So draw possible water level versus time graph for the three containers. So I'm gonna use blue for the flask, I'm gonna use green for the beaker, and I'm gonna use red for the graduated cylinder. So let's start with the flask. As you can see, let's say water pours in and it fills out the flask. You can see that on the bottom, it has much more volume, right, than to the top, because walls are tapered inside. So volume here on this level is more than volume here, right? And more than volume here, but here volume is the same. So basically what is happening from the beginning, water is not getting higher as fast as it's getting higher here because it has to fill out less volume. So basically we can represent the graph of flask up to this point when it becomes same as follows. So first it fills out slowly, then gradually increasing its speed, let's say like this, and somewhere where it reaches the top, where it becomes like same cylinder after this, right? Here, the rate at which it will be filled out will become constant, right? Because constant volume here in this interval. So from bottom to here, it was increasing slowly, then faster, faster, faster. And this exponential part represents it. And then we're filling up at the same pace because volume is the same at this part of the flask, right? Now let's pour it into the beaker. Pouring water into the beaker, and what we can see, the volume is big, but it's constant across the whole height of a beaker, right? So water level versus time graph should be just a straight line because rate at which we're filling up the beaker is the same across the whole interval. And finally, the graduated cylinder. What different about graduated cylinder with respect to beaker? First of all, it's much thinner, right? Much less area here, much less area. So much less volume to be filled out for each centimeter of the height, right? So what we're going to do, we're going to say that we're going to fill out the graduated cylinder same way we filled out the beaker, so at a constant rate, but this rate would be much, much faster. So basically, our graduated beaker gonna reach the same height much faster than the beaker. So like this, would be much steeper graph, but still with a constant rate of change. Do you agree with me? Yes. Do you see logic in my reasoning about rates of change? Do you see how they're connected to the real life, basically physics and everything that surrounds us? You can give an analogy with swimming pool. For example, when people filling out the swimming pool, they have to calculate how fast will they fill out the swimming pool. And for example, if some area more shallow or tapered, they know that here we have less volume, so it's going to be filled out faster, etc. Same case. And if we go lower, you can see that I was pretty much accurate in my representation. You see graduated cylinder, the fastest, the steepest hill, then the beaker, less steep hill, and flask increasing, and then gradually increasing at the same rate. Are there any questions about this at all? Okay. So let's do one more example. A cyclist is observed moving at a speed of 10 meters per second. She begins to slow down at a constant rate and 4 seconds later is at speed of 5 meters per second. She continues to slow down at a different constant rate and finally comes to a stop 6 seconds later. So we have to sketch a graph of speed versus time. Let's start with that. So we have speed axis and time axis. This is time, this is for velocity, speed. And cyclist is observed moving at a speed of 10 meters per second. So at moment of time 0, her speed was 10 meters per second. She begins to slow down at a constant rate and 4 seconds later is at speed of 5 meters per second. So for 4 seconds she was decelerating at a constant rate up to 5 meters per second. 4 seconds. She was decelerating for a constant rate of change. Then she continues to slow down at a different constant rate and finally comes to a stop 6 seconds later. So first time she was decelerating for 4 seconds and she covered 5 meters per second deceleration in 4 seconds. And then she decelerated for another 5 meters per second in 6 more seconds. Okay, 6 seconds. So I would even put it a little bit farther. So 6 seconds. So we can see that the slope is a little bit different, right? Let me move it even farther so it can be more obvious. Yep, like this. Yep. Do you agree with me? Do you agree that this graph would look like this? Oh, so I actually made a mistake if you didn't see that. So 10 seconds, right? Because second time she was decelerating for 6 more seconds. So altogether 10 seconds, right? Now we have to evaluate what is the average rate of change of the cyclist speed in the first 4 seconds. And that should be easy for us because we know that the average rate of speed, average rate of change calculated as a delta y over delta x between 2 points. And these 2 points are 0 and 4 seconds. So 4 minus 0 in denominator and 5 minus 10 in nominator. We started at 10 meters per second and finished at 5. So our rate of change is negative, and it's reasonable. So we have negative 5 divided by 4, which equals to negative 1.25, 1 and 1/4, right? This is our average rate of change in first 4 seconds. Do you agree with me? And question C is quite tricky. If you understand what you're doing, you're gonna see it right away. Because we know that she began to slow down at a constant rate for 4 seconds. So it's a statement that this interval has a constant rate of change. And question C asks us, estimate the instantaneous rate of change in speed at 3 seconds. Somewhere here, right? 3 seconds. But you're smart. You're smarter than this book. You're a smart student and you say, wait, why do I even have to spend my time on question C if I already know the answer? Question says that she was decelerating at a constant rate, which means average rate of change and instantaneous rate of change are going to be equal in this interval. Does everybody agrees with me? Here's this solution that they suggest. You can see that here they actually calculate the approximation for instantaneous rate of change, right? But they come to a result that instantaneous rate of change is the same as the average rate of change calculated in part B. This should not be surprising since the tangent line at x equals 3 has the same slope as the second line on the interval from 0 to 4. So one more time. Average rate of change, we know how to calculate it and we did it. For instantaneous rate of change, you have to write down the equation of the line for the first part of the graph, right? Because uh, in order to calculate the instantaneous rate of change, remember the general formula. Delta y over delta x equals f(x)(2) minus f(x)(1) divided by x2 minus x1. You cannot calculate the instantaneous rate of change without knowing the function that sets your rate of change. In this problem, you were giving with only the letter explanation of her speed, but you must be able to compound a function that would represent the part of a graph that you're interested in. For example, from 0 to 4 seconds, her graph is a straight line, right? Just straight line that joins 2 points. When x equals 0, function equals 10. And this coefficient, -5/4, is actually a slope of an average rate of change, isn't it? So because the general formula of a function, of a linear function, is y equals kx plus b, and you have to know how to construct this function. Please recall on your spare time on how to determine the function of a line, function of a quadratic function. This is what you were supposed to cover in grade 11. Okay? It's not very complicated, but it's good to refresh in your memory what K means, what does B means, etc. Here is one more example. Let's talk it through. And by the way, this Sunday, we're going to conduct our first test based on average and instantaneous rate of change and the characteristics of function. I will post the home assignment related to it in the Google Classroom. Please make sure to check it out after this class. And let's get to the example number 4. Using reasoning to represent and analyze a situation. Adam and his friend are testing a motion sensor. Adam stands 0.5 meter in front of the sensor and then walks 4 meters away from it at a constant rate for 10 seconds. Next, Adam walks 1 meter toward the sensor for 5 seconds and then waits for another 5 seconds. Okay. So draw a distance versus time graph for Adam's motion sensor work. Okay, so let's do it real quick. Distance let's say d, in meters, and time in seconds. So Adam stands 0.5 meters in front of the sensor at the beginning. Time equals 0. He's already 0. He's already like 0.5 meter away from the sensor. And then walks 4 meters away from it at a constant rate for 10 seconds. So 10 seconds, and he walked away 4 meters away from it. So half a meter plus 4 meters. So 4.5 after 10 seconds. And remember, at a constant rate, so just a straight line. Next, Adam walks 1 meter toward the center for 5 seconds. So another 5 seconds, so 15 seconds in total. He walks toward the sensor 1 meter. So 1 meter, it was 4.5, it became 3.5. We don't know if he walks here at a constant rate or not, but let's assume he walks here at a constant rate, so the line would be straight, right? This is another point. Adam walks 1 meter toward the sensor for 5 seconds and then waits there for another 5 seconds. So for another 5 seconds, he remains still and at the same distance from the sensor. So at moment of time 20 seconds, he ended up at a distance of 3.5 meters away from the sensor. On the drawing below, you can see that my representation is pretty accurate, even though I'm not following the scale. Just based on the logic that first he was getting farther away from the sensor, so the graph is growing because this graph of a distance over time. Then he was getting closer to the sensor, so the graph is decreasing. And then he was standing still, so the graph is just a flat line. Okay, what is the average rate of change in his distance in the first 10 seconds? So it's pretty easy to do again, delta y over delta x in the first 10 seconds, so from 0 to 10, so 10 minus 0 in denominator, and y difference is 4 meters. We basically know it from the question. He walked 4 meters away, so delta y would be 4. 4 divided by 10 will be 0.4 meters per second. That's the rate of change that he was walking with for the first 10 seconds. What are the instantaneous rate of change at first second and then 7th second? Again, based on the knowledge that if he was walking away at a constant rate, so this line just a straight line, and the slope of this line is same across it, at point of time 1 and 7 seconds, he had the same rate of change as an average rate of change in this interval, which equals to 0.4. Okay? What is the average rate of change in the next 5 seconds? So in the next 5 seconds, it would be negative because he was getting closer to the sensor. That would have some specific value. No, just use this formula to calculate it. What are the instantaneous rate of change at time equals 12 seconds and 14 seconds? So at 12 seconds, it would be equal to the average rate of change in this interval. I'm going to use a red color to highlight it. So instantaneous rate of change at 12 seconds and 14 seconds is going to be equivalent to the average rate of change here. Going to be equal to it. And what is the instantaneous rate of change at time 18 seconds? So after 15 seconds to 20, 18 somewhere here, and we know that at this moment of time, he was not walking at all. He was standing at the same distance away from the sensor. So we can say that the instantaneous rate of change at point of time 18 seconds equals to 0, because this is simply a horizontal line that has no slope. And finally, draw a speed versus time graph for Adam's motion sensor walk. It's a little bit different. This is a distance over time, and another one is a speed over time. So if he was walking away at a constant speed, it means this first part of the graph should be flat. And let's see how it's represented right here. So this is, oh, sorry. Move it to the right. So this is distance over time graph. And this is distance over time over speed graph. And you can see that if for the first 10 seconds he was walking away at a constant speed, what it means? It means that the graph of speed at this moment of time would be a horizontal line, isn't it? And then right after that, he was walking away with a constant speed again. So you can see that his graph of speed looks like a piecewise function that we covered in the previous classes. That jumps from one value to another, constant speed here, and then instantly constant speeds there. And finally, from 15 to 20 seconds, is not moving at all. So his graph equals 0 and just a horizontal line with y coordinate equals 0, right? So as such. Now we have two graphs. Time versus distance and time versus speed. And both of them we got from only verbal explanation of how he was walking. Isn't that crazy? Isn't that fascinating? So one more time. Time over speed is delta v velocity over delta t. And distance over time is delta d change in distance over delta t change in time. So two different graphs, delta v of delta t and delta p of delta t. And summary. In a problem that involves movement, a possible graph shows displacement, distance, height, or depth versus time. Distance, height, or depth is the dependent variable, and time is the independent variable. The rate of change in this relationship is speed, isn't it? Change in distance with respect to change in time. On a displacement, distance, height, or depth versus time graph, the magnitude of the slope of a second line represents the average speed on the corresponding interval. The magnitude of the slope of a tangent line represents the instantaneous speed at a specific point. As a result, observing how the slopes of tangent lines change at different points on a graph gives you insight into how the speed changes over time. We can see that this example, displacement is increasing, so we are walking away. So increasing line indicates that the displacement increases as time increases. Decreasing line means displacement decreases as time passes. And horizontal line means that displacement is not changing over the time. As well as increasing in speed. If the displacement graph is not a straight line, but rather an exponential function, it means the speed of our movement is increasing. We're decreasing, or we are walking away faster and slower, just as in examples that we are covered today. And finally, exercises for your homework. I'm gonna submit them later today. Make sure to prepare your questions by Friday. On Friday, we're going to conduct a support class where you can ask your questions and get prepared for test on Sunday. Is there any questions now? Our class came to an end. No? No questions? No. Well, thank you, Hala. Thank you for your solutions today. It was a great job from you. I appreciate it. Make sure to carry on to the next classes, and everybody else should join us. And it's really a big help for yourself at first place if you try to express your thoughts on material in class. Because when you speak, you learn the best. When you speak, when you say it out loud, when you make a discussion with other people about it, that's when you remember it the most. Okay, guys, I wish you all the best. Have a good evening, and thanks for attending today's class. Have a good one. See you on Friday.